Hi everyone, and welcome to this video lecture in which I will explain to you second order homogeneous ordinary differential equations with constant coefficients. Let me start off by giving you the general form of the equation that we are going to look into. That will be x double dot plus p times x dot plus q times x is equal to 0. So this is the ODE, P and Q being constant coefficients. And this second order ODE has two initial conditions. The initial value for x, which I will call x0, and the initial value for the velocity that I will call x dot 0. Alright, so let's try to solve this differential equation. What we can see is that because there are constant coefficients, we are looking for a solution x as a function of time, in which this function together with its derivative and second derivative forms 0. So based on our experience with first order ODEs, we are going to try an exponential function. So this is the so-called trial function, e to the power st, and this is based on our experience with first order ODEs, where we derived that the solution is an e power. So let's try this and see if we can find an expression for s for which this will work. So let's substitute this and its derivative and its second derivative in the differential equation itself. So the second derivative is s squared e to the power st. Then we have ps e to the power st plus q times x itself, qa to the power st is equal 0. So I can take e to the power st outside of brackets, and since this is non-zero for finite values of s and t, basically it can be cancelled, and we are left with the following algebraic equation: s squared plus ps plus q is equal to 0. And this equation is called the characteristic equation of the ODE. So this is the equation from which we should solve S such that the trial function is indeed a good solution. Now, since that this is a quadratic equation, there will be two solutions for S. Let me call them S1 and S2. And they can be solved using the quadratic formula. So we have minus a half p plus or minus, plus or minus a half times the square root of a p squared minus 4q. So indeed this produces two solutions for S, two roots of the characteristic equation. And that means that now the general solution can be written as a solution can be written as a linear combination of the two solutions. So x as a function of t can be written as c1 e to the power s1t, where for instance s1 is the solution with the plus sign, and c2 e to the power s2t, where s2 is then the solution with the minus sign. Alright, and the reason is that since S1 substituted satisfies the differential equation and S2 does as well, because the right hand side is 0, we basically are just adding two functions here that once substituted in the differential equation are both 0. So in general, the solution is any linear combination of them. Alright, and the coefficients C1 and C2 are determined by applying the boundary, not the boundary conditions, the initial conditions. So I will not do that here, but you can imagine that you can have two equations for two unknowns, namely the two initial conditions should be satisfied, and that determines C1 and C2. All right, so this is the general strategy, I would say. This will work. We have to, however, address one very inconvenient situation, and that is what happens when in the roots for S there's this square root. What happens if p squared is equal to 4q? What you see then is that this term underneath the square root is 0, so that both S1 and S2, they are equal to minus a half p. Okay, this situation is so-called a repeated root. Repeated roots. Like this. That is kind of awkward because then the general solution is C1 e to the power minus a half pt plus C2 e to the power minus a half pt. So this is twice the same function. So in fact that is only one solution. All right, so this is a bit of a problem. Only one function is produced from this method. And this is a problem because the general solution must consist of two linearly independent functions, because after all there are two initial conditions that need to be satisfied. Okay, so clearly e to the power minus a half pt is a good solution. What is the other one? What is the second solution? The second solution. Okay, we have a method for finding this second solution, and this is called reduction of order. That's the name of the method. Reduction of order. And I will talk you through now, and then we will discover what is this second solution. The idea is that we try for x as a function of t, now some function y as a function of t, which is likely going to be some kind of polynomial, but it could be any function, times this solution that we found. So that was e to the power minus a half pt. All right, and I'm going to, this is a try, of course. So hopefully if we do it in this way, we can discover what this function y is, and maybe from that produce the second solution. Now I will show you that this works. Let's first differentiate, because we also need an expression for x dot, which is then, I will drop the t now, so we have then that y dot times e to the power minus a half pt minus a half p times y e to the power minus a half pt by means of the product rule. And then for the second derivative, we have y double dot e to the power minus a half pt, and then we have the differentiation of the e power, so that is a minus a half times a p times y dot e to the power minus a half pt. So this is the derivative of the first term. Now for the derivative of the second term, I differentiate first y, so that will give me another times minus a half p y dot e to the power minus half pt. So that means I can simply cancel the half here. Let me erase that. Minus. And then we still have a plus 1 over 4 p squared y e to the power minus a half pt. Alright, so this is the trial function and its first and second derivative. Let's substitute that into the differential equation. Maybe I should rewrite the ODE here for convenience. So we have x double dot plus p times x dot plus a q times x is equal to 0. And we are considering the situation in which with p squared equal to 4q, right? So that's the condition that we have here, this special case. So let's substitute that, and I will group now the terms with the same derivative for y. So let's first group all the terms that we will have with y itself. Let me maybe change color. So here I have a term with y. Here a term with y is produced. And this original function contains y. Okay, so let's substitute that. We have then a quarter p squared plus a minus sign, that should be minus a half p, but that is multiplied by p itself, so that will be a quarter like this, plus a q times y e to the power minus a half pt. Okay, that's the first term. And now I will group all the terms that have a y dot. Let me do that with red. So here we have a term with y dot, and here we have a term with y dot. Let's group these. So we have minus a p, and then we have plus p times the velocity, so plus p times y dot e to the power minus a half pt. And then finally the terms with y double dot, that's only one term, y double dot e to the power minus a half pt. And this should be equal to 0. Well, as I did this, what you can already see is that this term with the y dot cancels, because minus p plus p is equal to 0. And the term in front of the y, the first term in between brackets, what do we have there? We have 1/4 minus 1/2, so that is minus 1/4 p squared plus q. Okay, but recall that p squared is equal to 4q. So that means that this term is 0 as well. So this entire equation basically reduces to y double dot e to the power minus a half pt is equal to 0. Well, for finite values of time, the e power is not 0, so this reduces to y double dot is equal to 0. Alright, this is a second order differential equation for y, and it is of the trivial kind. So, trivial. And the reason that it's trivial is that we can solve it simply by integrating twice. So we get as a solution for y, that y as a function of time is any linear function in time. Let's call it c1 plus c2 t, like this. Okay, so summarizing, we have tried for our solution x, y times this first solution, and we have solved that for a linear function of y, this will indeed satisfy the differential equation. So let's substitute that we found that the general solution for x as a function of time is now C1 plus C2 times t times e to the power minus a half pt. All right, so that means that using this exponential trial function that we started with, that initially that sounds like a good idea, and from that we produce for the specific case that p squared equals 4q. For that specific case only one root is produced, and that is the solution some constant times e to the power minus a half pt. Now, using this procedure of reduction of order, we were able to discover that the second solution is just the same as the first solution, but then multiplied by a factor of t. Now, this is something that we will see in future lectures as well. Sometimes we have to find a solution for repeated roots. So the normal method only produces one solution. We are interested in finding another solution. Typically, it is a good guess to just multiply your solution that you already found with t and see if that works. And for some cases that we will discover later on, this will indeed work. Okay. This was basically what I wanted to tell you about second order homogeneous ODEs. So once more, in short, in general, we try an e to the power st, and we solve the characteristic equation for s, and it produces two solutions. In the specific scenario that only one solution is produced, we can use this method of reduction of order to find the second one. So maybe let me also close off by boxing this solution. So this is the general solution of the ODE when S1 and S2 are distinct, and this is the general solution when S1 equals S2. All right, that concludes the lecture. Thanks again for watching. I see you next time.